So Descartes' rule of signs is just another way of eliminating some of the possible zeros that we come up with for our list when we do our P divided by Q possibilities. So we have, for Descartes' rule of signs, we have some polynomial, and I'm going to list it out, all the terms like we've been talking about. So we have a sub n, x sub n plus a sub n minus 1, x sub n minus 1 plus, and we have a bunch of terms. And then we have a sub 1x plus a sub 0. So there's our polynomial that we've been talking about. Descartes' rule of signs tells us, and we want a sub 0 not equal to 0 for Descartes' rule of signs. So we have some constant number out here at the end. We don't end with something multiplying x. We have some number. Descartes' rule of signs tells us several things. The number of positive real zeros of f is equal to the number of sign changes in f of x. And we'll talk about what that means with a couple of examples in just a second. It's equal to the number of sign changes in f of x, or less than that number by a multiple of 2. And another way of saying this is that it's less than the number by an even integer. And we'll do a couple of examples. It sounds more complicated than it is. And Descartes' rule of signs can also tell us that the number of negative real zeros of our function is equal to the sign changes in f of minus x. Or less than that number by an even integer. And another way of saying this, we could say a multiple of 2. And sign change just means that consecutive terms here have the opposite sign. That's what we mean by a sign change, is consecutive terms have opposite sign. So we can use Descartes' rule of signs to give us an idea of how many real zeros we have. If we had a huge list of possible zeros, and Descartes' rule of signs tells us that there's only one positive zero, and we test 1 and that's our positive 0, then we know we don't have to test any more positive numbers. The rest of them have to be negative. And we can use the second test to tell us how many negative real zeros there would be. So sometimes Descartes' rule of signs can really help us eliminate the number of possible zeros that we choose from. So let's look at a couple of examples of using Descartes' rule of signs. And this is not something that's going to help you out picking out to eliminate the number of real zeros. That's the whole idea of Descartes' rule of signs. So let's look at a couple quick examples, and that's all I want to say for today. Let's say we have 7x f of x equals 7x to the third plus 3x squared minus 5x plus 9. So we want to look at the number of times the signs change in f. So here, this is positive to positive, doesn't change there. From here to here, I have one sign change. And here we go negative to positive. So there's a sign change. So f of x has two sign changes. Change from positive to negative, then negative to positive. So f of x, by Descartes' rule of signs, f of x has two positive real zeros, or it's less than this number by a multiple of 2, or no positive real zeros. So those are our two possibilities. So if we come up with a huge list of real zeros, of possible zeros of our function, and we look at Descartes' rule of signs, Descartes' rule of signs for this particular function tells us that there are either 2 positive or 0 positive real zeros. So we can, once we find 1, we know that there's only one more positive real zero. And if we test, if we find one that's negative, then we know the other one has to be negative because it could have no positive real zeros. Yes?
What if you were to have something like negative x cubed and minus x? Would that be easy to find?
Remember, Descartes' rule of signs says we have to have this constant term out here.
If that was out there, what if there's like something missing? Would that count as a positive sign change?
If you with Descartes' rule of signs, I think you need to have a term represented for each power. So if you're missing one, then you wouldn't be able to use Descartes' rule of signs. So you'd have to have a term for each power. Because you could say you could say that's negative 0 something also. So that's a little ambiguous. So you need to have each term represented. Okay? So let's look at f of minus x. So f of minus x, I'm just going to plug minus x in here. F of minus x to the third, it just changes the sign, turns out negative. So I get negative 7x cubed plus 3x squared plus 5x. If I plug negative x in here, it changes that sign, plus 9. So let's look at the sign changes here. I have 1 there.
Why doesn't the
We're squaring a negative. When we square a negative, the sign turns positive. So we have 1 sign change there, no sign change there, no sign change there. So this tells us that f has 1 negative real zero. and I can't reduce 1 by a multiple of 2. So f has either 2 positive zeros or no positive zeros, and it has 1 negative real zero. So this can help us eliminate some of the zeros once we start listing them out and picking them from our list. So let's look at another example with Descartes' rule of signs. Yes?
So what would the answer look like? What would we put down as an answer to a problem like that?
So the problem would say list the possible positive and negative, list a number of possible positive and negative real zeros. So you would say 2 positive zeros or no positive zeros and 1 negative real zero. And that would be the answer. But usually what you're doing with Descartes' rule of signs is to help you solve problems like what we did on the board, just to eliminate some of our possibilities so we're not having to test 6, 7, 8 different numbers to figure out which one is a zero. Okay? So let's look at negative 7x to the third plus 3x squared. Oh, that's not what I want. That's my f of minus x. Let's look at x to the fourth minus 2x cubed plus x squared minus x plus 1. So this is my function. So we're going to look at the number of sign changes. I have 1 there. I have 1 there. I have 1 there. And I have 1 there. So this has 4 sign changes. So f has 4, 2, or 0 positive real zeros. And let's look at f of minus x. F of minus x, if we plug in minus x, this stays positive. So I have x to the fourth. Minus x cubed, I'm going to get a minus, so that'll change that sign. Doesn't change that sign. Change this one to a positive. So how many sign changes do I have here?
1, 2.
All of these are positive, right? F of minus x has no sign changes. So this tells us that f of f has no negative real zeros. So our list, when we come, this one would be fairly easy to solve because I have a 1 at the beginning and a 1 at the end. So our factors, our possible real zeros are just plus or minus 1. Descartes' rule of signs says that it can't be negative. It has to be positive. Questions on Descartes' rule of signs?
So that answer is just 1 then? Positive 1?
And positive 1, since it has to have 4, 2, or 0 positive real zeros, this tells us that can't be negative. So our 1 is our only positive possibility. So it's going to be a repeated root. So it would be like x minus 1 to the 4th power or something like that. Because we have to have 2, but they can be the same. They can be repeated. So it could be x equals 1, 2, or 4 times over. Okay? All right, so that's all I wanted to say about Descartes' rule of signs. Yes, did you have a question, Jesse? What the answer would be, right? So, and this one's a pretty easy one because we just have a 1 here and a 1 here. It's pretty easy to pick our possibilities. Descartes' rule of signs comes in handy when you have a long list and you can eliminate a lot of those possibilities from your list. All right.